Hey class, welcome to our Algebra as a game, little added homework thing with some worksheets. So I don't want you to be too worried about there being tons and tons of math. There will be more math in the beginning as we cover a few algebra concepts that we'll be using. The trigonometry part, it's hard to count that as math because that's more going outside and having fun. But hopefully the math will be more fun. The stuff that you're going to have to learn in pre-algebra or algebra right now, or if you've already taken those, that's great. It'll be kind of a review, but it's going to get way cooler as we're calculating how to take trips in space-time and finding new particles and finding out that there is a wave equation for ourselves. We think of ourselves as one thing, but we're actually also a wave. We won't be calculating that for other reasons, but there's going to be a lot of cool applications of the math, which I hope is going to make it worth the doing the math if you're not a mathy person. And the other thing not to worry about is there will be more hands-on stuff than math in this class. So we're really trying to make it mostly hands-on Einstein stuff. In fact, Mrs. Johnson and I are writing a book out of this Einstein class with Joy Hakeem that we're hoping will be a maker's guide to relativity and quantum physics. So we're trying to make it as hands-on as we can. So when thinking about our algebra, I was thinking about this. My daughter, when she was learning algebra, my mother, who's taught middle school for 30 years, really recommended this thing called hands-on equations. And so we used it, and that is really what got me thinking of algebra as a game, and it was a lot of fun for her. Unfortunately, it's not free. They do have an app right now, but we used the actual physical hands-on. It was game pieces that you could add. So the blues would be X and the whites would be Y, and then you had positive numbers and there were green dice for negative numbers, and you just put them on either side of this big equal scale, right? And so the idea is the scale has to stay equal at both sides, which brings us right to the biggest rule of algebra. So if you added too much to this side, the scale would tip and you'd have to balance it by adding things on the other side. So the biggest rule of algebra is, as long as you do the same thing on both sides of the equal sign, you can do whatever you want. You can use this to make your stuff more complicated, or you can use it to make your stuff less complicated. So let's see how that goes. And we're going to use some pretty heady sciencey stuff to do that. Okay, so let's look at F, oh, sorry, gotta get my F is equal to M times A, which is force is equal to mass times acceleration. This comes from Isaac Newton's 3 laws of motion, which we will talk about in our next class. So this is one of Newton's 3 laws of motion. Force is equal to mass times acceleration. Now, if I wanted to make this more complicated, but still say the same thing, I could add 27 to both sides. I don't know why I would want to add 27 to both sides, but I just do. If I add on this side, I'm going to have F plus 27. And that's going to equal mass times acceleration. And those things are going to have to be multiplied together, and then plus 27. This is still going to work out to be the same as what I had before. Because if somebody comes along and says, well, you can make that more complicated all day long, but your homework is to solve for F and figure it out. I was like, oh, well, I better stop making it more complicated. Let me just subtract that 27 from both sides again. As long as I do the same thing to both sides of the equal, I'm good. Got to get down to business now, and I'm back to F is equal to mass times acceleration. The dot is just a way of saying times. So I could also make it more complicated by multiplying or dividing. Let's say I want to multiply, and I'm going to put the times like this, both sides by 3. then I get F dot 3, or we would usually write that as 3F is equal to 3, and I'm going to use the dot this time, times mass dot A. Okay, I've just made it more complicated, but I can divide both sides. That's an A, not a 9. I should make that better. A. I don't have my Wacom working today, so I have a new computer and it's not. So I can divide both sides by 3. Now this brings us to an interesting thing because now I've turned this into a fraction. Let me just clear this stuff above so we can see what's going on here. When I divide both sides by 3, I can just put a little bar under it, turn this side into a fraction, turn this side into a fraction. Okay, now look at this. This is an added little something that we are actually going to talk more about next week. But when something's on the top and on the bottom of a fraction, 3 over 3 is the same as saying 1. So so we can actually cross these 3's out because there's 1 on the top and 1 on the bottom, because that's the same as just saying 1. So I am back again to F is equal to M times A. Okay. So that is doing the same thing to both sides of the equal with a little simple idea. Now, we can do the same with our letters. Let's go back to F. Oop, I just keep forgetting to go back to that. F is equal to mass times acceleration. Okay, in our worksheet that you're about to do, you need to find the acceleration, how fast something is going to speed up. Okay, so we need to solve for A, which means get the A, this is a dot here meaning multiply. We need to get the A on one side by itself. To do that, we have a times here. To get that times away, we do the opposite of times. So M times A, the opposite of that would be divide by M. Now, because I did it on this side to get rid of the M, I have to go over here and do the same thing on this side. The M over the M, I can cross them out because that becomes 1. M over M is 1, so that's just 1 times A, which is the same as A is equal to F over M. Perfect. Okay. If you were in my Newton class, and again, if you weren't in my Newton classes, this sounds interesting. I'm happy to help you go through that as well. We did a really important thing called the ideal gas law, and I hope you remember because we went over it every day for our whole term. P V, pressure times volume, you can put a dot in there, or it's kind of implied, is equal to the amount of something, which is N, times the ideal gas constant times temperature. And we use a larger T usually in this equation so it doesn't look like it's time. Now, I've got times on one side, I've got times on the other side. The great thing about PV equals nRT is we can use these to move this stuff around and solve for anything. Let's say I want to find the temperature of my ideal gas. Well, I go over here, I want to get the T by itself. I divide by N times R. And I go over here and I divide by N times R. Well, these R over R is 1, so this goes away, and N over N is 1, so this goes away. So I have solved for temperature. PV equals over N, R is equal to the temperature of an ideal gas. Now, it sounds kind of complicated. I put up the ideal gas law and I told you pressure, volume, number, ideal gas constant, and temperature. And boy, that is some complicated math and science to understand. But just by knowing your basic rules of algebra, you are able to solve for and use the ideal gas law. Even if you don't know what the ideal gas constant is, you don't know anything about these other things, just your basic algebra, and you are already a powerful chemist because you can use the ideal gas law to solve for any of these things. Okay, let's go on to our next rule. When you take the square root of things, there is a plus answer and a minus answer. Okay. When we take the square root of things, so a square root is, as most of you guys know, many of you guys know, so when you square something, 3 times 3, that is equal to 3. We write this as the exponent squared. So we call that the square. And then, which 3 times 3 is also equal to 9. Now if I take the square, but here's the other thing. A negative times a negative is a positive. Why that is a big deal. I'm writing a math book too, and it's in there. Proving that is interesting. So if anybody wants to do that in office hours, that is a fun thing to do. Negative 3 times negative 3, and negative times negative is a positive. So that is also equal to 9. So when something comes along and we're hit in math class and the teacher gives us a problem and says a is equal to the square root of 9, right? If they come along and say, oh, that a looks like a 9, let me choose x. X is equal to the square root of 9. The most correct answer is not x is equal to 3. That's a good answer, but that's not the most correct answer. We say x is equal to plus or minus 3. Plus or minus 3. Now this is going to become a big deal when we go through our derivations of certain things, because, and where this got to be a big deal, let me delete, there we go. Where this got to be a big deal was there is a certain equation that a man named Dirac was looking at. Dirac. And Dirac was looking for the energy of an electron. And he got this equation, and I'm going to use our don't look down technique. He got down to an equation that had E is equal to the square root of something. Okay? Now, I'm just going to use my don't look down technique right there, and we're going to say it was, we're going to see what's under there later. But he gets down to an equation that says the energy is equal to the square root of something. And lots of people have been there before, right? But he was looking at this, and lots of people have been there before and said, well, obviously energy isn't negative, so it can only be the positive outcome of this, right? So they would get the energy, of a electron. When we write things, well, I'm terrible at writing it. This is the electron. I'm just going to misspell it so it's shorter. Must be equal to the positive version of what's coming out of this blue box, right? So that was what everybody had been doing. They were only giving the positive answer. And Dirac comes along and says, well, my Algebra 1 teacher would be very disappointed. I'm not sure if that's exactly what went through his head. My Algebra 1 teacher would be very disappointed if that's the only answer I gave. So what happens if we look at the negative version of this? And what he found was a whole new particle. It is a particle that is the opposite of an electron. Where an electron is negatively charged, the positron is positively charged. So this finding the plus and minus of a square, and it was something that all the physicists of the time had missed. So this is, again, we have to go back to the simple things. By going back to good pre-algebra and algebra 1 techniques, Dirac found a new particle. He found antimatter. So we'll go back and we'll talk about this when we get to our particle stuff, but I want to keep this in your mind as we're going through simple algebra. Is going to be very important. Okay, I'm going to have to continue this in another recording, so I'll be right back with our third rule of algebra.